Imagine a river so choked with dead timber that you could ride a horse across it. Not a bridge, not a dam, just a solid wall of tangled trees, packed so tight that soil collected on top, bushes took root, and entire forests grew out of the water. The Red River in Louisiana had exactly that problem for nearly 1,000 years. The logjam stretched over 150 miles, from bank to bank, surface to riverbed. Explorers in 1806 described it as an almost impenetrable mass of cedar, cottonwood, and cypress, so tightly bound that a man could walk over it in any direction. And every spring, the river shoved more trees into the pile from above, while the lower end slowly rotted away. The raft just kept growing. Towns upstream were cut off from trade. Farmers could not ship their cotton to New Orleans. The entire region was trapped behind a wall of wood and mud that no one had the tools to break through. That would change because of a single invention, a strange double-hulled steamboat with a mechanical arm on its bow that could rip a 60-ton tree from a riverbed like pulling a weed from a garden. That machine was called a snag boat, and the man who built it, a self-taught riverman from the Pennsylvania frontier, was about to become the most important river engineer in American history. His name was Henry Miller Shreve. Born in New Jersey in 1785, raised on the Pennsylvania frontier, Shreve spent most of his young life working on barges and keelboats along the Ohio and Monongahela rivers. By the time he was 30, he knew every bend, every sandbar, and every danger on the western waters. He also knew what was killing the boats: snags, fallen trees that lodged in the riverbed just below the surface, invisible until a steamboat hull slammed into one at full speed. Between 1821 and 1860, snags wrecked 593 steamboats on American rivers. That was more than fires, more than collisions, more than boiler explosions. The rivers were highways, yes, but they were highways full of hidden spikes. Think about the scale of that number for a moment. Nearly 600 steamboats destroyed by trees hiding under the water in a span of about 40 years. That does not even count the ships that hit snags and limped to shore with smashed hulls, or the ones that avoided total loss but spent weeks in repair. The insurance industry barely functioned on western rivers because the risk was so high. Captains pushed upriver knowing that any bend, any stretch of slack water might hide the tree trunk that would punch through their hull and send cargo and passengers into the current. By the 1820s, the federal government was desperate. Congress authorized a $1,000 bounty for anyone who could prove a reliable method of clearing snags from western rivers. Earlier attempts had used manpower, ropes, and mule teams pulling from the banks. Some crews tried lashing two steamboats together with a crossbeam between them and driving onto snags, using the beam as a crude lever. It worked occasionally, but the boats were not designed for it. Hulls cracked, engines broke, the snags often won. Shreve had been watching these failures for years, and he had a different idea. What if you built a steamboat from the ground up, specifically for the job? Not for carrying passengers or freight, but for destroying the obstacles that were sinking everything else. A machine whose entire purpose was war against the river bottom. In 1827, Shreve accepted the post of superintendent of Western River Improvements at an annual salary of $5,000, less than he could make on a single profitable steamboat trip to New Orleans. He had already broken the Fulton-Livingston monopoly on Western River navigation, fought to open the Mississippi to free commerce, and brought supplies to American troops during the War of 1812 aboard the steamboat Enterprise. He knew what the rivers needed. He took the pay cut because he wanted to build something no one had ever built before. The Heliopolis was launched in 1829. It looked like nothing else on the water. Two separate steamboat hulls, each 125 feet long, were permanently joined at the bow and stern with heavy beams. Between them, Shreve installed a system of windlasses, levers, and rollers, all powered by the boat's steam engine. The idea was brutal and elegant at the same time. You drove the twin hulls straight into the snag, straddling it. Then the steam-powered machinery gripped the tree and ripped it out of the riverbed. If the tree was too big to pull, a sawmill mounted on the deck cut it into pieces right there on the water. Shreve sailed the Heliopolis to Plum Point on the Mississippi, one of the deadliest stretches on the entire river. The bend was so sharp that snags collected there constantly, wrecking boats year after year. In just 2 days, the Heliopolis cleared the entire stretch. Shreve reported back to Washington that the performance far exceeded his most sanguine expectations. The machine worked, it actually worked, and that was only the warm-up. Because the government had a bigger job in mind, the Great Raft of the Red River. Nobody was sure exactly how old the raft was. Some estimates put it at 800 years. Others said it had been forming since the 12th century. What everyone agreed on was the scale. By the 1830s, it stretched over 160 miles. At some points, the mat of logs had grown so thick that horsemen rode across the top, and full-grown trees waved above the waterway from soil that had accumulated on the rotting wood. The raft dammed the river so completely that the water spilled over its banks and created entire lakes. Caddo Lake, Cross Lake, Lake Bistineau, all of them exist because the Great Raft backed up the water until new bodies of water simply formed in the lowlands. In 1832, the Secretary of War ordered Shreve to clear it. He was given 159 men, his snag boats, and not nearly enough funding. The work could only happen 3 or 4 months out of the year. In spring, floodwaters crashed downstream, carrying fresh trees that rebuilt the raft faster than crews could tear it apart. By midsummer, water levels dropped so low that the boats could barely move. Shreve's crews attacked the raft from the lower end, ripping logs free, soaring through the tangle, letting the current carry debris downstream. By 1836, they had cleared 71 miles. One single snag pulled by the Heliopolis during those years contained 1,600 cubic feet of timber and weighed at least 60 tons. Shreve declared the Red River open. The city that sprang up at the head of the newly navigable stretch was named Shreveport in his honor. He was among the investors in the Shrevetown Company that founded it. For a brief moment, it looked like the problem was solved. The Red River was free, commerce could flow. Congress gave him almost nothing for maintenance patrols. Within a few years, the raft started growing back. The spring floods of 1839 pushed fresh timber into the cleared sections, and by the early 1840s, much of what Shreve had opened was clogged again. One scheme after another followed over the next 30 years. Private contractors tried and failed. Military engineers attacked sections of the raft with limited budgets and limited results. Some reports suggest the government spent over $500,000 on removal efforts that were constantly undone by the next flood season. In 1872, Lieutenant E.A. Woodruff took his turn. He used Shreve's snag boats, but added new vessels, boats outfitted with circular saws to cut through submerged logs, and boats with cranes to lift debris from the edges of the tangle. When nothing else worked, Woodruff's crews turned to nitroglycerin, blowing apart what they could not pull free. What they could not untangle, they simply destroyed. It took years of combined mechanical and explosive assault. But by the mid-1870s, the Great Raft was finally permanently broken. The snag boats opened the rivers, but opening them was only half the problem. You also had to make them deep enough. By the middle of the 19th century, American commerce depended on river depth the way modern commerce depends on broadband speed. A channel that was 9 feet deep 1 month might be 4 feet deep the next after a season of silt washed in. Ships ran aground, ports lost access, whole economies stuttered because the river bottom kept rising. This was where dredging became critical, not just pulling trees out, but physically removing the mud and sand that nature kept putting back. The first American suction dredge was the General Moultrie, built in 1857 and put to work on the Charleston River in South Carolina. She had a single suction pipe about 18 inches in diameter and a centrifugal pump mounted on her deck. Her hopper could hold about 118 cubic meters of material. The concept was straightforward. Suck the mud off the river bottom, store it in the hull, haul it somewhere else, dump it. The General Moultrie proved the concept could work. Then she sank in 1858. The technology was promising, but fragile. Meanwhile, the biggest dredging challenge in North America was staring the federal government in the face. The mouth of the Mississippi River. Silt from half a continent washed down through New Orleans and piled up in the delta, creating sandbars that blocked the largest ships from reaching the Gulf of Mexico. Government efforts to deepen the channel had been underway since 1837. None of them worked. By the 1870s, the problem had become a nightmare for commerce. New Orleans, which had once handled more shipping volume than New York City, was being strangled by its own river. Enter James Buchanan Eads. Self-educated, brilliant, and stubborn in the way that only someone who has walked the bottom of the Mississippi River in a homemade diving bell can be. Eads had spent his 20s salvaging sunken steamboats using a contraption he built from an open-ended barrel and an air hose. He made a fortune pulling cargo off the river bottom. During the Civil War, he designed and built a fleet of ironclad gunboats for the Union. After the war, he built the Eads Bridge across the Mississippi at St. Louis, using structural steel in ways no American engineer had attempted before. It opened on July 4, 1874. Then Eads turned his attention to the mouth of the river. His proposal shocked everyone. Instead of dredging the channel with machines, he wanted to make the river dredge itself. He proposed building 2 parallel jetties, long walls made of willow tree trunks bound together and weighted with stone, extending far out into the Gulf from the banks of the river's South Pass. By narrowing the channel, the jetties would force the water to move faster. Faster water would scour the bottom, cutting the channel deeper without a single dredge bucket touching the mud. Congress was skeptical. The Army Corps of Engineers thought he was crazy. They had their own plan, involving a canal at a different pass and, naturally, more dredging. Eads offered to finance the work himself until the channel reached 20 feet. If it failed, the government owed him nothing. If it succeeded, they would pay him incrementally for every additional foot of depth, down to 28 feet, plus $500,000 a year for 10 years of maintenance. The Corps sent their own engineer, Charles Howell, to dredge Southwest Pass, while Eads built his jetties at South Pass, 30 miles away. It became a race, and the results were not even close. Eads completed his jetties in 1879. The river did exactly what he predicted. The narrowed channel accelerated the current, which blasted the silt out to sea and carved a shipping lane 30 feet deep. For all practical purposes, New Orleans had an unrestricted outlet to the ocean. Howell's dredging operation at Southwest Pass never reached its target depth. Eads proved something important. Sometimes the most effective dredge is the river itself, if you know how to aim it. The southernmost point of Louisiana, at the tip of the Mississippi, is still called Port Eads. He died at 66, before he could fully appreciate how completely he had changed the course of river engineering in this country. But here is the catch. The jetty method only works where you have a strong current you can accelerate through a narrow channel. Most rivers cannot be tricked into doing the work for you. Shallow harbors, sluggish tributaries, wide delta flats where the current spreads out and drops its load of silt across miles of riverbed, those problems need brute force. Steam-powered machines, physically scooping, sucking, and blasting sediment from the bottom, remained the backbone of American waterway maintenance for the next 100 years, and the machines kept getting bigger. The Army Corps of Engineers built and operated its own fleet of steam dredges starting in the 1860s. The Essayons, launched in 1868, was one of the first. She was built specifically to clear navigable channels at the mouth of the Mississippi. Her design was unusual and ultimately not very successful. She was mechanically unreliable and spent much of her career being repaired and upgraded. She was sold off by the Corps in 1882. The name, though, stuck. Essayons is the Corps' motto, a French word meaning "let us try," and they kept trying. By the early 20th century, the Corps had developed a specialized type of vessel called the Dustpan dredge. It worked like an enormous underwater vacuum cleaner. A wide, flat suction head was lowered to the river bottom, and steam-driven centrifugal pumps inhaled the sediment, shooting it through discharge pipes to wherever it needed to go. These machines could move staggering volumes of material. The William M. Black was one of the finest dustpan dredges ever built. Launched in 1934 by the Marietta Manufacturing Company in Point Pleasant, West Virginia, the Black was 277 feet long and 85 feet wide. She was powered by two 600-horsepower reciprocating steam engines that drove her 25-foot paddle wheels, each one weighing 32 tons. A separate 1,300-horsepower triple-expansion steam engine ran the dredge pump. When all three engines were running at full capacity, the Black could devour 80,000 cubic yards of river bottom in a single day. She burned up to 7,000 gallons of fuel oil every 24 hours to keep that operation going. The Black was not just a machine. She was a floating village. Her crew of 49 men lived aboard for weeks at a time. The main deck held a machine shop, storerooms, a drying room, a kitchen, separate mess halls for crew and officers, and 14 staterooms including quarters for the captain and the chief engineer. Two massive boilers produced up to 40,000 pounds of steam per hour. The smokestacks carried the insignia of the Army Corps of Engineers. The noise inside the Black when she was dredging must have been extraordinary. 3 separate steam engines running at once, the grinding roar of the suction head scraping the river bottom, the rush of sediment and water through the discharge pipes, all of it vibrating through a steel hull that doubled as the crew's living quarters. The men slept in staterooms a few dozen feet from the boilers. They ate their meals in a mess hall that shook with the rhythm of the paddle wheels. The work ran around the clock during dredging season, with crews rotating through shifts that blurred the line between day and night. For nearly 4 decades, from 1934 to 1973, the Black worked the Mississippi, the Missouri, and other western rivers, opening navigation channels, excavating pilot channels and boat harbors, and pumping earth fills for levees. She also performed emergency dredging during floods, when sandbars shifted overnight and threatened to strand entire fleets of commercial barges. She was one of the last steam-powered vessels the Corps of Engineers ever operated, a machine from a dying era doing work that would never end. Her sister ship in spirit, the Captain Meriwether Lewis, was launched a few years earlier in 1931, also built by Marietta Manufacturing. The Lewis was even bigger, 268 feet long, with a standard crew of 52. She could dig to a depth of 20 feet at a speed of 150 to 200 feet per hour, all powered by her 25-foot steam paddle wheels. When her 3 steam engines were running full bore, she consumed 6,000 gallons of oil a day. These were serious machines doing serious work. The rivers they dredged carried the lifeblood of the American interior. In 1979 alone, more than 15 million tons of grain, petroleum, steel, and fertilizer passed through a single lock and dam near Dubuque, Iowa. That commerce moved because the channel was deep enough. The channel was deep enough because dredges like the Black and the Lewis had been eating the river bottom for decades. The same steam-powered dredging technology that tamed the Mississippi and the Missouri also helped carve one of the most ambitious construction projects in human history, the Panama Canal. When the French began digging across the Isthmus of Panama in 1881, steam dredges were already part of the plan. The earliest French dredges worked at Basse Obispo in 1884, chewing through tropical earth and rock. The biggest challenge was the Culebra Cut, a 12-kilometer trench through the Continental Divide. The geology fought back constantly. Landslides buried equipment. Clay too soft for steam shovels had to be sluiced away with water. The French managed to lower the summit by only about 17 feet before financial ruin and disease ended their attempt. The Americans took over in 1904 and brought a level of industrial violence that dwarfed anything the French had attempted. At the peak of construction, 6,000 workers swarmed the Culebra Cut alongside dozens of steam shovels, each one numbered and tracked like a weapon on a battlefield. Twice a day, all work stopped for blasting. More than 600 holes, packed with dynamite, were detonated in a single day. Over the life of the project, 27,000 metric tons of dynamite were used, roughly 60 million pounds. The ground shook so constantly that the engineers on the cut practically lived inside an earthquake. Then, the steam shovels moved in to scoop out the loose rubble, And when the cut finally reached water level, the dredges took over to finish the job. Landslides made the work unpredictable and terrifying. The International Board of Engineers had assumed the rock walls would hold at steep angles. They were wrong. In some places, the rock started collapsing at a fraction of the projected height. One engineer described standing on ground in the cut that rose 6 feet in 5 minutes with a smooth, almost invisible motion. The earth could push upward from below and swallow entire pieces of equipment. Records from the American period of construction document 5,600 deaths, and the actual number of workers killed was likely higher because many West Indian laborers lived outside the canal zone and their deaths were not always recorded. The Corozal, launched in 1911 by a Scottish firm, was the largest and heaviest dredge in the world at the time. She was built specifically for the Culebra Cut. In December 1913, the Corozal became the first ship to sail through the completed cut, shortly before the canal opened to traffic the following August. Landslides kept coming even after the canal opened, and dredges stayed on duty clearing the debris. The Panama Canal Dredging Division was established at Gamboa in 1936 and has been there ever since, because the cut never stops trying to fill itself back in. Working on a steam dredge was not glamorous, and it was not safe. The boilers that powered these machines were the same basic technology that was killing people all across the country. Steam boilers in the 19th century were, to put it plainly, bombs waiting for a reason. Water from rivers carried minerals that left deposits inside the pipes, narrowing them and blocking heat transfer. Steam built up behind blockages that no one could see. Engineers often ran the boilers at pressures far above what they were designed to handle, because higher pressure meant more power and faster work. In 1880 alone, 159 boiler explosions were recorded in the United States. Between 1880 and 1890, more than 1,200 boilers blew up. The Sultana disaster of 1865, when 3 of 4 boilers on a Mississippi steamboat exploded and killed over 1,500 people, remains the worst maritime disaster in American history. The deaths of more than 300 people from steamboat boiler explosions in the spring of 1838 had already pushed Congress to pass the first national safety regulation in the country's history. But even after the Steamboat Act of 1838 required inspections and safety equipment, boilers kept exploding. Between 1841 and 1848, 70 more explosions killed 625 people. It took the stronger Steamboat Act of 1852, which mandated pressure testing, safety valves, and licensing for engineers and pilots, to finally start bringing the numbers down. Crews on steam dredges worked next to pressurized boilers, producing tens of thousands of pounds of steam per hour, on shifting water, in all weather, for weeks without a break. Every day on a steam dredge was a calculated bet that the iron holding all that pressure together would not give out on your shift. The dredge crews also faced something less dramatic, but just as grinding. The work was monotonous and endless. Rivers do not stay dredged. Silt comes back. Sandbars reform. The channel you cleared last month is half full again this month. The Corps of Engineers understood this from the beginning, which is why federal law authorized ongoing snag boat operations on the Upper Mississippi, the Illinois River, and the Minnesota River as far back as 1888. This was not a project with a finish line. It was a permanent commitment, and it still is. During the Mississippi River drought of 2022, the Army Corps of Engineers ran dredges around the clock for 6 straight months. At some points, 3 vessels were operating 24 hours a day, 7 days a week, traveling to choke points near St. Louis, dropping their suction tubes to the riverbed, inhaling sediment, and piping it to disposal sites. One Corps official described the process as being like a giant vacuum cleaner. A single modern dredge can fill an Olympic-sized swimming pool with river bottom roughly every hour. The steam is gone now. Diesel and electric power replaced it decades ago. But the work is the same work that Henry Shreve started in 1829, and the rivers are the same rivers. The William M. Black sits in dry dock at the National Mississippi River Museum and Aquarium in Dubuque, Iowa. She was designated a National Historic Landmark in 1992. The Captain Meriwether Lewis rests along the Missouri River at Brownville, Nebraska, where she houses the Museum of Missouri River History. She became a National Historic Landmark in 1989. Both ships are open to visitors who want to walk the decks, see the boilers, and stand where the crews stood while they fed coal and oil to the engines that ate the river bottom. These machines carved the channels that commerce still flows through today. They broke apart a logjam that had been growing since the Middle Ages. They deepened the mouth of the Mississippi so that New Orleans could reach the sea. They helped slice a canal through the spine of 2 continents. None of it was glamorous. Most of it happened out of sight, on muddy water, in brutal heat, with dangerous machinery and crews who lived on the boats for weeks at a time. There is a strange paradox in all of this. The better the dredge crews did their jobs, the more invisible they became. A well-dredged river looks like it was always that deep. A cleared channel feels natural. Nobody stands on the banks of the Mississippi and says, "Thank goodness someone vacuumed the bottom of this river last month." But that is exactly what happened. That is what is still happening right now, somewhere on the inland waterways, on any given day of the year. The rivers look natural. They feel like they have always been where they are, as wide and as deep as they are. They have not. The depth you see was purchased with steam and sweat and iron, 1 scoop of mud at a time, by floating machines that most people have never heard of. Henry Shreve's twin-hulled Snag boat, the Essions, and her unreliable pumps, the General Moultrie, which proved an idea and then sank, Eads and his jetties that made the river do its own work, the Dustpan dredges that ate 80,000 cubic yards of riverbed in a day, the Carousel, slicing through the spine of Panama. Each one was a step in a chain of engineering that made American commerce possible, and each one has been almost completely forgotten. The next time you see a barge sliding down the Mississippi loaded with grain, or a container ship clearing the mouth of a river on its way to open ocean, the reason it fits in that channel is because someone sent a dredge there first. Probably more than once. Probably last month. If you found this story interesting, go ahead and hit subscribe so you do not miss the next one. Drop a like if you learned something new, and leave a comment telling us which forgotten machine from American history you think deserves its own video.